quickly. Listen very carefully and understand it's not difficult. There's just a lot of calculations that have to be done and a couple of things to remember or to note as we're going through this thing. So I'll try and highlight it as we're moving through it. Okay, so can you all see my screen? Right? So in the book on page 8.4, right? You can go to 8.1 quickly, where I've made sort of copies for the appropriate parts, right? In the discussion, in the first part of it, they talk about the type of walls and what is important on page 8.3, very, very important, is the drainage. You can design the wall very well, right? But if the water cannot escape from your soil, it now adds an additional pressure. So let me try and illustrate what I'm saying. Say I have a soil on this side. So I have a soil here, right? On the back here. That's where the soil is that I'm retaining. Are you with me? And the pressure due to that soil on the retaining wall will look like this, a triangular distribution, right? The retained material will exert a pressure density times K times H. That's the stress. You multiply it by height divided by 2 and you get a force, right? Okay, but what's going to happen with water, if it is saturated, you're going to get plus an additional pressure, right, due to the water. Now that'll make it quite big. That'll increase the force dramatically, right? So the thing to do is to get rid of the water. How do you get rid of the water? Is you need to provide a drainage system behind the wall. So you need to have some kind of soil in the back here that is porous, that the water can go down to a pipe, that agricultural drain that catches it at the bottom. And in addition to this, what you do is you take a weep hole, and people don't understand that the weep hole just isn't just left as a pipe in the wall. What you have to do is you have to put 19mm stone or something like that. So you take stone and you wrap it in a bidum cloth. So you make a cubic sort of shape, about 200 odd, right? And you wrap this with bidum cloth. Bidum cloth it allows the water to come in, right? But it keeps the stone in position. And you plug this behind your weep hole, right? This was one of the old ways of doing it. So you put a lump of this stuff behind the weep hole. So what happens is the soil doesn't get into the weep hole and clog it up. So it's always free for the water to escape, okay? And then of course you have an agricultural drain which picks up the water at the bottom, and it mustn't just run behind the wall. It's got to come out and go to wherever the drainage system is. Does everybody understand what I'm saying? So you'll notice that now when we had these unusual or storms and rains, the first problem is walls collapse. And the reason they collapse is because the drainage of the wall hasn't been taken into consideration. Okay, all right. Does that explanation help you? I hope. Okay, so now one thing that can happen to the wall is it can slide. All right, so we check this under normal working loads. That's the important thing. It's done under working loads, so not ultimate limit state. And we see that we must have a factor of safety of 1.5. Okay, soil failure. This is bearing pressure story. Again, working loads. All right. And then we've got fracture of wall elements. This is ultimate. So we designed the stem and the base for bending, but here we do an ultimate limit state check. Just something in the book is that it emphasizes a heel and a toe, so it emphasizes this kind of wall. But in practice, walls generally, I'm saying boundary walls is where you come across retaining walls there's one of two things that happen. One is you create a retaining wall where you actually, right, you're doing this. So that's option one. All right. The other option is, so there's your boundary. Are you with me? And you want to, you have some kind of sloped land, and you want to put in a flat space for whatever reasons you may want to, driveway or whatever it is. So you need to do that. By the same token, so this is happening inside your property, right? By the same token, you could have this happening where you on this side now, on the other side, and you want to retain the soil on that side. Are you with me now? Okay, so now the property, your property is on this side. Do you follow? So you've got a bank and you want to cut the bank. So you've got a bank there and you want to cut it. And so this is the two most common situations that you find for retaining walls, right? And a lot of the times for smaller heights, you can actually get away where you use a brick skin or blocks, right? Which form your shutter for. So for small construction sites, not major things, you could do it like this. So you have brickwork on either side, and then you've got the concrete coming inside. Between that, you pour the concrete. Right, so you put your concrete in here. Sorry, wrong color. Where's the concrete? Green, I don't want it. Okay, so you're putting the concrete in here and into the foundation. Are you with me? So that's, it's very common. You can use a block. And what they also do is they sometimes use a block on this basis in plan. So this in plan would look like your concrete. That's, I'm talking about the wall now, right? And your brickwork on each side. Are you with me? But sometimes what they also do, and we do this in masonry design, so this will come up in the honors thing. What we do is we put column that is reinforced, column that is reinforced, the wall in the front there. So you can do this with blocks, and you can fill the blocks with concrete, and you can put the steel inside the blocks. So you get like a counterfort type of wall, okay? So for smaller heights, like up to 2 meters, you sometimes might go for that instead of a full reinforced concrete wall. So it depends on the costing, etc. So that's a practical aspect, okay? So what I'm saying to you is this picture that you see in the book is not really the ideal. The ideal is a bit different, is that there's normally no toe. Okay, angle of internal friction. This is the angle at which the material will support itself. The value of phi is normally between, sorry, theta is between 30 and 45. Reynolds, the old Reynolds has this table, for example, and it tells you that if you had a gravel, the angle of friction would be 35 to 45. If you had a sandy, loose soil, it will be that. And it tells you the density, bulk density. So you've got this kind of stuff, all right? That's cohesionless material, contain granular material. Okay, you've done soils, geotechnical engineering, so I'm not going to go into all of that. And then they've got clays here in the bottom, all right? And then they've got a cohesion, you have to do it by test. So there's a table there which just gives an idea of the different kind of soils and what the properties they have. Okay, so where were we? Yeah. All right. So soil parameters you will get from your geotechnical side. Soil density also, value is normally upwards of 15. Sliding friction mu. Mu is tan theta, right? He's put this recommendation, tan theta minus 5 is often assumed. Some people just take tan theta, some may take this value. Ground pressure, again, something that is given to you, geotechnical side. All right, applied pressure, active soil pressure. The pressure from the soil behind the wall will become active as it begins to move forward. The distribution of pressure will be triangular. So what you're saying is you have triangular distribution of pressure, okay, behind the wall due to the soil, right? And P is K, so the active soil pressure maximum at the bottom is going to be Ka times the density of the soil times the height. Now that's your height, okay? So that gives you a stress. You got 0 at the top, right? So you can see that if I take Ka times density times H, right? And then I multiply it by H over 2, I'm going to get the force. And then, of course, I need the lever arm distance when I'm calculating the moment, okay? But essentially, that's what we're saying. Density times K, active soil pressure, okay? And then we're going to convert it to a force, right? Okay, so this is according to Rankine's theory, which I hope you did in geotechnical engineering. Where the backfill is level behind the wall, K is 1 minus sine theta over 1 plus sine theta, where theta is equal to angle of internal friction of retained material, right? Okay, so that is normally given to you in the situation of the exam or the tests, right? For a sloping backfill and an angle of phi measured from the horizontal. So phi is going to be, so you've got, what you're saying is behind your wall, instead of a horizontal fill, you've got a sloped fill. Okay, so you got that situation. So that angle is phi, right? So that's phi. Just be careful with the phi and the angle. Some books will swap these things around. Okay, so K is cos theta. Now it changes to n plus 1, where you're bringing in the value of phi. Okay, the angle of this that the soil is sitting at above. All right. Passive soil, this is quite common. Oh, by the way, the other very common thing is to use these blocks. You might have noticed. Okay, they use these blocks, and Loffelstein was the original one, and then they put them on the bank, sort of stepped, right? They have a whole manual about how to set this thing up and the angle, etc. And then you need a foundation at the bottom. Okay, this kind of thing is also common, but we've seen in the recent storms, some work pretty well, and a lot of these problems with this one. In some cases, it was found that the blocks were just made, so they were still fresh. They were still fresh concrete. They hadn't had time to cure properly, etc., and they were put onto site, and that became a problem. So just be careful. You have to know what you're doing when you're doing something like this, right? It's not in our syllabus, as I said. Maybe we can bring it into the honors. Passive pressure is that pressure which will develop when the wall push against the soil in front of it. The distribution of pressure will be triangular, and we gave this. So that's the active pressure that is being retained, right? And then on the other side, you might have some soil in front of the wall, and this is called passive. Now you notice that the passive formula is the opposite of active. 1 minus sine over 1 plus sine. Passive is 1 plus sine. So here you might get something like 0.3 or 0.4, and here you get something like 3. So it's a big difference. Okay, so make sure you're doing the right thing. Surcharge pressure. The pressure resulting from a uniform surcharge. So you could have behind the retaining wall some load on top of the soil. We call it a surcharge. And that will be PW times W, pressure due to the surcharge, and surcharge kilonewtons per square meter. And here's the thing about water pressure, is that you're supposed to get rid of it, not leave it there. Okay, then this is something that has been covered in mechanics, right? It was a topic in mechanics as well. So it's a pretty straightforward thing. We're not going to go into the derivation. We're going to look at the eccentricity. So in other words, you've got the force, you've got the weight, and you've got a resultant force. And the thing is whether it falls within the middle third or outside the middle third of the foundation. If it falls within the middle third, you've got compression throughout. If you've got greater than the middle third, then you're going to have some tension. Okay, so you will get different formulas. This formula kicks in when you have tension. So now you've got to ignore the tension, and your pressure diagram is going to look like that with that part where you had the tension being ignored. But if you have your stress, if your eccentricity lies within the middle third, so it lies within the middle third, then you're fine. Okay, then you get compression throughout. So you covered that in mechanics, and we can't keep going back to work that has been done before. All we can do is remind you, and that's it. Resulting pressure distribution. So that's the due to the surcharge. The triangle is due to the soil, your minimum maximum, and your passive pressure in the front, right? To calculate the pressure distribution below the base, we simply apply the basic combined stress formula. Force over area plus or minus m upon z, all right? M is equal to W times eccentricity. Section modulus is going to be BD squared over 6. We'll come to the numbers. So it's L squared over 6 because we take B as 1 meter, all right? The formula may be written as P is equal to W over L, 1 plus 6 eccentricity over L, is the distance at which the resultant force acts from the center of the base, and may be calculated as follows. In the book, you've got it there. Sorry, I think I skipped a page there, page 8.8. On page 8.8, or did I put it before this? Oh, I thought I had it here. I think the page has got a bit mixed up. So there's your page 8.8 there, right? And there's your P maximum. Okay, so again, we'll look at this in detail. Design approach. The stability checks and calculations are the same for all types of retaining wall. The only difference in design being the analysis of the ultimate forces and moments, all right? A 1 meter length of wall is considered for design purposes. So we take 1 meter length of the wall, and all elements of a wall are generally designed as for slabs. Now, also the building regulations give you information. So you can use the building regs for small retaining walls, like a meter or something like that. And you don't have to design it. You can just go to the building regulations and follow the guidance that is given there. Just be very careful. Like you've got a building and you're going below ground with one of the floors. So the ground floor is below ground. So part of your wall that is supporting the upper structure, the roof, etc., has to be considered as retaining. So what I'm talking about is something like this. So let's say you have a double-story building. Okay, so you got a ground floor slab, and then it goes down to your foundation, and then you got another floor here, for example, and goes up, and you got your roof, right? Now this, the way it's built, maybe there's soil here and you've excavated. So this part of it becomes retaining. Do you understand what I'm saying? So you have to design it as such, and you have to must be very, very careful, because the biggest problems here is water. Okay, and often people forget about this, and then the builder will hit a shortcut, and because he's not too concerned with the developer. And later on, you now find you've got a lot of water on the inside, moisture and dampness and all those kind of things. So be very careful. You've got to know something about the water condition of the soil, whether you have rising damp, the water table is high, that kind of thing. So you've got to look at all of that. So structures is not just done in isolation, it's combined with your knowledge and your skills in water and geotechnical engineering. Okay, so thickness of wall, these are some guidelines. I will show you some other ones also. So they say the thickness of wall at the base should be about 0.09 H, depth of the base, roughly that number, toe about that, heel about that. Okay, so this is just a guide. And then Greg gives you a sketch of the different symbols, capital H for height, small p for the depth of the foundation, Q for the height of the wall. A is the full height of the wall, Q is the height to the flat part of the fill, and then of course you got the slope part sitting on top of that. B is the soil that is put on top of the foundation in the front. C, D, F, and L as is shown, okay? And then very nicely is given you some formulas, pretty straightforward. If you want the force, it's Ka times rho times h squared. We discussed that. I just discussed that with you a little bit earlier. Where's the lever arm? And that's the moment. So we look at the stabilizing. That's your forces, your backfill, your bank, your cover, stem. So he's given it to you in formulas for each of these. I'm going to go through it in the example, but I still like to understand what I'm doing. Design a suitable reinforced concrete cantilever retaining wall where the difference in ground level is said to be 3.7. So that's a big wall. Okay, when you go above 2 meters, it's you need a good reinforced concrete. The other option, of course, you've seen where you're cutting for highways, and that is they have a facade that is vertical and they use rock anchors going back to hold that facade. So that's another form of retaining. Sheet piles are another form of retaining, but we don't have the time to go to all of them. We're just looking at a typical cantilever retaining wall. Okay, the soil behind the wall is to be inclined at 10 degrees. It'll carry a life surcharge of 2. So this example is quite comprehensive because you've got, besides retaining, you've got a surcharge and you've got a bank which is sloped, which is not flat, 25 MPa concrete, high tensile steel. Theta is given as 35. Okay, so that's your angle of internal friction, right? So please just make a note on your book. Angle of internal friction is 35. Density is given as 16. Mu, the coefficient of friction, is taken as 0.4. So it's given, you don't have to use 35. So if you took the 35, but not always the case, and you took tan, what do you get? So if you take tan of 35, you get 0.7, which is quite high. If you take tan of 30, you still get something quite significant, which is 0.57. So it's not always tan theta, it depends. But here mu is given as 0.4, so they got it out of some geometric thing. Working ground pressure must not exceed 120, right? So using those guidelines that he gave you, you assume now that you're going to have the following. Retained soil is 4 meters, then you've got the base dimension, the thickness of the wall at the top. If you look at the top, it's smaller than what was required, right? It said you need 0.09 times 8. Remember, in your situation, you're given the dimensions, okay? So this is when you're doing it from scratch, okay? Overturning, now we've got a sloping bank, so we plug in sine squared theta. Sine squared theta will be sine squared, sine squared, and this is 35 degrees, minus 0.5, and this is tan. This is where your 10 comes in, I think the slope, and times sine, and this is 70 degrees because it's 2 times 35. And then you put a square root sign over the whole thing. And if you calculate this, you'll come out to 0.4961. Okay, Ka. Now, because you got this, you're not using 1 minus sine over 1 plus sine. Using, this is page 8.6, using Ka is equal to, because of the slope, right, of the ground, you're using cos squared theta over n plus 1. So you got cos, not cos squared theta, cos theta over n plus 1 all squared. So cos 35 divided by that 1.49 n plus 1 gives me 0.3. Question?
Yes, where does that 70 come from?
70? is 2 theta, 2 times 35. So this one here, this one is 2 times 35. Okay, if you take sine 35, go to your calculator, sine 35, right? It's 0.5735. Square it. It's 0.329. I'm just putting it roughly, right? 0.329 minus 0.5 times 10. Make sure you're in degrees, please. Is 0.088. I'll just do it to 3 decimal places, okay? Times sine of 70. Sine of 70, that's sine 2 theta. It's 0.93, let's say 0.94. Okay, so n is equal to that. So n is equal to, you take this whole thing to the power half. What do you get? So you get 0.329 minus brackets 0.088 times 945, close bracket. Okay, and you've got, wait a minute, what have I done? 0.088 times 0.945 is 0.08 something. So you're subtracting it from 0.329. So 0.329 minus that value, I get 0.245, square root of that, and I get 0.495. I get 0.4958, which is 0.496. Okay, right? So you all got that? Okay, 0.496. Yes. Okay, right. Now we take that in and we plug it in this because we got a slope. If we didn't have a slope, it was flat. If it was flat, if you didn't have this, so you just had a wall with a flat fill at the back, then your Ka, remember, is not that. So please, you must need to make a note of these things so you don't use the wrong things. 1 minus sine over 1 plus sine. Okay, that's what K is equal to. So very different Ka, depending on whether it is sloping or it is flat. So don't just look at the example. For those who just don't do anything and come into a test or a question with just following the book, then they're going to be in trouble. Backfill 0.3 times 16 times 4.4 squared. You notice this 4.4, just be careful. We're doing it for working load. We're going right to the bottom because the overturning takes place here. It turns about that corner, if you follow what I'm saying. So the wall is going to rotate. Do you understand? It's going to rotate about that. Do you follow what I'm saying? So I've got to go right to the bottom. Okay, right to the bottom of the foundations. Sometimes you'll get a key. If you have a problem with friction, you can introduce a key. So you can put into the soil here. So this will increase your passive pressure, but we'll talk about that when we're dealing with sliding. Okay, so just to highlight that we're going top of soil to bottom of foundation. Okay, right, so 0.3 times 16, density times 4.4. So Ka times density times the height squared divided by 2 because it's a triangle. Remember that? Okay, 46.46. What is the lever arm? You take 4.4, 1/3 of it. It's a triangle, correct? So 4.4 divided by 3 is 1.467. Are you okay with that? Okay, surcharge is 0.3, the Ka, times the surcharge, which is kilonewtons per square meter, 2 kilonewtons per square meter times the height. Simple. Okay, so this is 2,64, and the lever arm is 2.2 because it's in the middle. Remember, this is the triangular one. So please just put diagrams on your page so you know what you're doing. This one was that, and this one is due to the surcharge, which is rectangular, which is in the middle. This is 1/3, remember? Okay, right? So You add it up here, you've got the force. Set it out like this in a table, then it makes your life easier. F is equal to 49.1. If I sum these two numbers, okay, that's what I get there. And multiplying by the lever arms, I get a bending moment, which we call MO, for overturning, which is 73.97. This is not factored. Okay, please remember this part, not factored. It's working loads. Okay, not factored, very important. Stabilizing. So you've got the weight of the soil and the surcharge, which are pushing this thing over. That stuff plus that, which is giving you that, and that's causing this thing to overturn, right? As a moment, force times distance. What is resisting it is the weight of the foundation, the weight of the wall, and the weight of the soil. All this is acting, can you see, in an anti-clockwise, whereas these were acting, that the restraining is acting in a clockwise direction, and the active pressures from the soil and the surcharge are creating a bending moment, which is anti-clockwise. So it's opposing one another. So we call it the overturning moment and then the stabilizing moment. 16 density times 1.6, the foundation width, right? So you got that 1.6 there. So that's where the soil is sitting here on top, right? 1.6. So you've got 1.6 times 4. The height, 400 is the foundation, so 4 meters. So what's the soil above it? 102.4. Okay, kilonewtons. 0.5 times 16 times 6 squared times tan 10. So that's the bank, right? 0.5 times 16. Right, density times, so it's half, it's a triangle, remember? 16 times 1.6 squared times 10 of 10, all right? So you're taking the amount of soil, oops, where's this thing? Uh-oh. So you're taking the amount of soil, you've taken the backfill as a rectangle, and that has become triangular, right? And now you're looking at this piece on the top, okay? And that's what you're doing here. So 10 of 10 times 1.6, okay? We'll give you the height, and then 1.6 divided by 2 times 16. So you get the density of that one is 3.61. Cover, 16 times 0.3, that's cover is in the front. 16 times 0.3 times 0.5 is 2.4. Just something very important with cover, right? You got this cover in the front here. Please remember that when they do the wall, you're now depending on this, right? So you mustn't backfill completely without putting this thing back on. So ideally, when you come up with your starter bars and you've come up here somewhere and you're starting to backfill, so you don't backfill this whole thing once, you do it in layers, okay? Right? So you put it in layers, and as you're putting it, please don't forget you need to put it in the front as well, okay? Otherwise, when you're looking for your passive pressure, then you must, if you don't have it, it's like that. And of course, if you have the soil there, then it's a lot better. It gives you a bigger passive pressure. Do you follow what I'm saying? Okay. All right. So cover is what goes on the other side. 2.4 stem rectangle, stem triangle, stem base, right? And then the surcharge, which is 2 times 1.6. And as I said, the surcharge is a rectangular one. Okay. So 2 times 1.6, 3.2. And you get the lever arms. Okay, 1.65 because of the triangle, 1.917. Where does that come from? 1.917. Where does it come from? You've got thing on the top there. Okay. All right. So it comes through from the surcharge side. Sorry, due to the slope bank, I mean, and that gives you, so you take 4 meters. Well, not 4, yeah, 4 meters. And what is that? A function of 4 divided by 1.917. and it gives you 2,08, so it's like in the middle of it, right? The middle of the 4 meters, so that is also taken halfway, roughly, 1.917 or 2. Okay, and then you've got, where is it, the next part? Cover, 0.25. That's straightforward from the bottom. So you've got the 2 meters there, and then you're taking it on the bottom, right? Because your overturning is happening there. You follow what I'm saying? So you're measuring it from there, so 0.25, stem rectangle 0.75, stem triangle 0.6, and then the base. So you've split the wall up. Suppose the wall was like that. Okay, so you split it up into a rectangle and a triangle. Okay, base 1.225 surcharge, as we said, and you got the load, we call it W, the total weight, and the moment multiplied by these lever arms, 230,23, ms divided by mo, the moment due to all of this stuff stabilizing, divided by the moment due to overturning, you get 3.11, which is greater than 1.5. Sliding, you got Kp, right, which is the passive pressure, as I said in the front, 0.396, and you see you're taking 0.7 here. That means you're assuming the soil is in the front, they're full. So 14.47 mu, your coefficient of friction times your load, right? Mu times N is the frictional force. N here, the normal force is your W, right? The weight of all your stuff. And that gives you 65.14. So sliding resistance over sliding force. Sliding resistance comes from the passive resistance and the friction together. Of course, in a soil where there isn't friction, then you don't add this part. Depending on the cohesion, that's something else. Divided by sliding force is 49.1. There's a book by McGinley, and in that book they cover examples with granular soils and other type of soils. So just have a look at that at some point. No, it's not important now, not for our subject per se, but in practice it will be. Okay, so a reference for you, please write it down, McGinley. There's a book, Reinforced Concrete. Just check that. And in that book, you will find examples of retaining walls, and it takes into account the different soils, okay? Cohesion and cohesionless soils. Soil pressure, eccentricity, L over 2, 2.45 divided by 2. So that's the foundation. 2.45 divided by 2 minus M stabilizing minus M overturning divided by W. I get 0.266. That's the eccentricity. L over 6, 2.45 divided by 6.408, which is greater than the eccentricity. Therefore, the resultant falls in the middle third. So you can say E is less than L over 6 if you like. E is less than L over 6. L over 6 is the middle third, if you follow what I'm saying. Okay. So just in case you're not seeing this, you got foundation. Let's say it is 1 meter. I'm just using an example, right? 1 meter. So you want it to fall within the middle third, right? So you want it within the middle third. So the middle third will be L divided by 3. So this is L divided by 6. Do you follow? On each side. So that's where the L over 6 comes from, because it's L over 3 combined. Okay, so 0.408 is greater than the eccentricity, so it's fine. So eccentricity is less than the middle third, falls inside. P is equal to W over L, 1 plus 6 eccentricity. So therefore I can use this equation and I get 23.2 and 109.7. Now I'm not doing this in detail. This was done in mechanics, but it's very, very straightforward. You put the eccentricity, you put the length W over L, and there you have it, plus or minus. So smaller answer, bigger answer. bigger answer must be less than 120. So you have satisfied the requirements for bearing pressure, right? You satisfied it for overturning, okay? And you satisfied it for sliding. You check that you have a factor of 1.5 at least, okay? And so those were all working values, no factors. Now, when it comes to design at the ultimate limit states, then you've got to apply factors. Now, this is recommended 1.2, 1.6, 1.4. In fact, it's very confusing because when you do reinforced masonry, the factors are different to reinforced concrete. So you just have to keep that in mind. We've got a new loading code, and the new loading code tried to make it standard. What has happened is one code has been revised and the other one hasn't. So the factors are a bit different in masonry and in concrete. Masonry, I mean brickwork, blocks, things like that. So we use those for retaining walls as well. So be very careful. But at this point in time, we haven't been exposed to that. As I said, we're looking at those topics in the honors, because we said the most common material that is used is reinforced concrete and steel. And then, of course, in buildings, it comes in that you use masonry, brickwork, sometimes as a load-bearing material, sometimes to help you with a retaining wall. So that timber, pre-stressed, all of that comes in, is looked at in some of it or all of it in the honors program. So we can't cover everything. I mean, we've got limited content because we're trying to create a graduate. He's sort of well-rounded. He's not a specialist in anything. He's just a rounded graduate, knows something about water, something about soil, something about transport, something about structures, okay? And then you have to grow it from that point on. So backfill, yes?
Can you please just help me understand the terminology of pre-stress when you say it's pre-stress? Is another word that you can use to
Yeah,
understand.
no, what you're simply doing is, so you take a slab, we normally reinforce it, right? So we put our steel in it. Sorry, let's get rid of this thing. Okay, so I put our reinforcement inside there, right? Are you with me? Now, what happens is with pre-stress, you have an anchor on one side and a jack on the other side, okay? And you stress this thing, so you know that it's going to deflect like this when you have a normal load. With pre-stress, you want to create the opposite effect to counter it. You follow what I'm saying? Okay?
Yes.
So that's pre-stressed. Unfortunately, we don't cover any pre-stressed concrete in our normal. It's quite common in slabs, and it's quite common in bridges. I mean, you couldn't do concrete bridge design without pre-stressing, right? Because the spans are very large, so you want to create resistance from that pre-stress. It's very dangerous because you can imagine there's large forces, very thick cables. When there's a bridge being constructed, you must try and have a look. It's quite complex, it's curved, there's a lot of things that come in, and the forces are very large. And if something slips, that cable will take everything behind it. So I was lucky early in my career that I didn't design a bridge or anything like that, but I worked on a site and I was on the earthwork side. But I watched the bridge being constructed and the pre-stressing being done, etc. So at least I got some idea of how it's done, right? Very common in slabs now, it's becoming where they want to make the slab thinner, so they pre-stress it, okay? But it's a specialist topic and it doesn't come in for our stuff here. So we took what we had before, backfill all those numbers from above. Okay, we took it from here, same numbers. We just brought it in, back here, and then we multiplied by the factor of safety. Now you notice those three, I've got the 1 point, sorry, my line's gone a bit funny here. Okay, so what I'm saying to you is those three there. Have 1.4 as a factor, and the rest of the concrete stuff has 1.2, and then the surcharge gets a 1.6. Okay, now you don't have a surcharge in every situation. You don't have a sloping bank in every situation. So you've got to see what you have and apply the appropriate things. Okay, so that gives you now the ultimate. This is now the W ultimate. Remember, we're working with the working loads before, right? So P W over L 1.6. Do the eccentricity again. Eccentricity at the ultimate limit state is 0.268, and you check minimum, maximum based on that. Okay, you get this diagram. So in terms of time, I think we should stop here and we should start with this part, the ultimate design. Okay, once you've sort of more or less understood the first part. So what I would like you to do is you had one foundation to do for me, which I hope you've done. I gave you a column. I've given you a foundation tutorial, which I hope you've done. I want to cover that tomorrow. And then I want you to take the retaining wall question, okay, that is given to you in the tutorial pages, and start with it up to the point where we get the soil pressure and the sliding and overturning. So the normal unfactored stuff. Okay, so I want you to look at that, please. And I'll also try and do one more with you. Okay, because I want to try and finish off this week so you're free, left with your other things. So very important. Tomorrow I've set a lecture at 2 o'clock. Is that okay? I looked at the timetable. Drawing ends then, correct? Hello, can I get some feedback? Drawing ends at 2, from what I've seen on your timetable. Is that correct? Hello, can somebody tell me something, please?
Yes, I think that's not.
Okay. Is there, are you having transport today? But I think you guys have got some water thing to hand in tomorrow, okay? Is it right?
Yes.
Okay, so then I won't impose anything on you today, but by tomorrow, please, you must try and get that stuff done so that in the afternoon we can look at the foundation was given to you long ago. It should have been done this weekend. Okay, so that should have been covered. I'll give you a bit of a chance tomorrow to do the retaining wall first part, and then we'll take it from there. All right?
Sir.
Yes.
I see here we did not cover the sport foundation and the other parts.
No, we can't cover it. There's no time for it. So there are some things you're going to have to do self-study. Everything in the book is not in the syllabus.
Oh,
We
okay.
won't test you on the, we're only going to test you on a spot foundation with moment, and we're leaving out the, what you call it. We can't cover all of it. Even in flat slabs, we're just going to stick with what was in the book. I've given you additional stuff. Remember, I told you it's very useful, but I've given it to you, and we can't even go back to it. We can only do the basic flat slab stuff that was in the book.
Okay.
All right.
Yeah.
Okay. And I'm trying to restrict it, so we'll talk about the scope later this week. All right. Let's first finish our work. So I hope you just give me the foundation one for tomorrow, which you should have done by the weekend, and then we can move on with the retaining wall and finish that, and we're done. Okay. All right, so maybe I'll look at another last lecture on Friday, and then after that you can we can talk as required on a one-to-one basis. If we feel there's still something that needs to be done, maybe we can meet after that as well. But I'm looking at one more on Friday. I just wanted to see who's doing what on Friday. If any of the other lecturers are using, I just need to confirm it, or they're not. From what I've heard, everybody's done except for myself. Okay. All right. So we stop here. And I will see you tomorrow. Okay, those of you who haven't collected that flat stuff, Flat Slabs notes that I got copyright for you from, please collect it. I mean, it's from your money that you've paid for.
Yes, sir.
Yeah.
Is this example hand up on page 8.14 or no? I mean 8.13, or it's continue? It's still the same question.
Same thing is continued.
But now here they are assuming the concrete and the soil, all of that.
What are you talking about? Are you talking about
On
this
page
page?
8. Yes.
What about here? What are you asking me? Sorry.
Because I can see the. Oh no, it's fine. I see it.
Okay.
Nothing has to change.
All right. Nothing's changed. It's the stuff that was taken from before, but you're just applying the factors to it. Okay.
Okay. Yes, sir.
All right. So we stop here and we meet again tomorrow. You got any questions, you can raise them after this, okay? So let me stop the recording first. And register, very important.